Assalamualaikum and greetings everyone. This session is designed to equip you with a deep understanding on introduction and general considerations to retaining wall structures. Retaining walls are more than mere structures. They are engineered solutions to complex geotechnical problems. These systems allow us to stabilize slopes, preventing landslides and soil erosion, optimize land use in hilly or uneven terrains, protect infrastructure from natural hazards. What is a retaining wall? A retaining wall is a specialized structural system engineered to counteract the natural tendency of soil to move due to gravity. The purpose of retaining wall is to stabilize soil in situations where slopes would otherwise fail or erode. Basically, there are three core components of a retaining wall. Number one, wall structure, the visible element that directly resists soil forces. Number two, foundation. It will transfer loads to the ground and ensures overall stability. And number three, drainage system, essential to manage water flows and prevent pressure build-up. Key functions of retaining walls. Retaining walls play multiple critical roles in geotechnical engineering. Number one, support sloping ground. By holding back soil, retaining walls create safe and stable surfaces for construction. Number two, water management. Integrated drainage systems reduce hydrostatic pressure, preventing wall failure. Number three, create usable land. Transform steep terrains into terraces for agriculture, infrastructure, or urban development. Number four, enhance aesthetics. They contribute to landscape design by integrating structural functionality with visual appeal. Types of retaining walls. Retaining walls are classified into four main types, each suited for specific conditions. Number one, gravity retaining walls. Relies on its own weight to resist lateral forces. Constructed from materials like stone, concrete, or masonry. Limited to lower heights due to stability concerns. Number two, cantilever retaining walls. Uses reinforced concrete and base slabs for support. Efficient for medium to tall walls. Number three, anchored retaining walls. Incorporates steel tiebacks or anchors for additional stability. Ideal for deep excavations or heavily loaded walls. And number four, mechanically stabilized earth walls, MSE. Combines soil with layers of geosynthetics to create a composite structure, widely used in large-scale projects like highway embankments. Engineers choose the wall type based on site constraint, soil properties, wall height, and economic factors. Gravity retaining walls. Gravity retaining walls are among the oldest and simplest types of retaining structures. Stability comes from the mass of the wall and its wide base, constructed using heavy materials like stone or precast concrete blocks. Advantages: easy to construct with minimal equipment and aesthetic flexibility. Natural stones blend with the environment. Limitations: require significant space for the wide base, unsuitable for tight urban areas, and limited to low height applications due to their reliance on mass for stability. For example, small-scale gravity walls are commonly seen in landscaping, providing visual and functional support to garden terraces. Cantilever retaining walls. Cantilever walls are reinforced concrete structures designed for taller applications. Engineered principle: the vertical stem resists lateral soil pressure. The base slab comprising the heel and toe, counteracts overturning moments through cantilever action. Design considerations. Soil analysis to determine lateral pressures and ensure adequate reinforcement. Incorporation of drainage systems to prevent hydrostatic pressure. Applications: medium to tall walls in urban developments and retaining structures for bridge abutments. For example, cantilever retaining walls were extensively used in the Petronas Twin Towers project to support basement excavations and manage heavy traffic loads on surrounding roads. Anchored retaining walls. Anchored retaining walls are designed to handle high lateral loads, often in deep excavations. Anchors or tiebacks are drilled into the soil and tension. These anchors counteract soil pressure, allowing for thinner walls. Advantages: effective for tall walls exceeding 10 meters, reduced material usage compared to gravity walls. Challenges: complex installation requiring specialized equipment, risk of anchor failure if not properly tensioned or inspected. For example, the construction of the Grand Paris Express subway system relied on anchored walls to stabilize deep excavations in soft soil. Mechanically stabilized earth walls. MSE. MSE walls are an advanced retaining solution combining compacted soil and geosynthetics. Advantages: cost-effective and quicker to build than traditional concrete walls. Environmentally friendly as they use minimal concrete. Applications: embankments for high-speed rail projects. Retaining walls in areas with seismic activity due to their flexibility. For example, in the Delhi Metro project, MSE walls were used to stabilize embankments and reduce construction time while maintaining cost efficiency. Soil principles for retaining walls. Understanding soil mechanics is essential for retaining wall design. Number 1, shear strength determines the soil's ability to resist sliding. Engineers use direct shear tests to measure this property. Number 2, permeability affects drainage efficiency and hydrostatic pressure. Number 3, lateral earth pressure includes active, passive, and at-rest pressures, all of which must be accounted for in the design. Accurate soil characterization is achieved through geotechnical site investigations, including borehole sampling and in situ testing. Groundwater considerations. Groundwater management is critical for wall stability. Number 1, groundwater levels are a key aspects of geotechnical and hydrogeological studies, as they significantly influence soil behavior, construction practices, and environmental sustainability. The groundwater level refers to the upper surface of the saturated zone in the ground where the soil or rock pores are fully filled with water. Number 2, drainage systems. Weep holes and granular backfill improve water flow. Geosynthetic drains can enhance drainage in high water table areas. Number 3, waterproofing. Membranes protect walls from water ingress. Number 4, geotechnical investigation. It involves collecting, analyzing, and interpreting data about the physical properties of soil, rock, and subsurface conditions at a proposed construction site. This investigation ensures the design and construction are safe, stable, and cost-effective. Foundation design for retaining walls. The foundation of a retaining wall is the structural element that bears all loads and transfers them safely to the underlying soil. A poorly designed foundation is the most common cause of wall failure. Key considerations in foundation design. Number 1. Bearing capacity. The soil beneath the foundation must be capable of supporting the weight of the wall and retain soil without excessive settlement. Tests like the standard penetration test or plate load test are performed to evaluate this. Number 2. Foundation type. Spread footings, suitable for small to medium walls where the soil has adequate bearing capacity. Piled foundations, required when the soil is weak or compressible. These piles transfer loads to deeper stable strata. Number 3. Depth of foundation. The foundation must be deep enough to prevent issues like frost, heave, or scur. In coastal areas, this often requires additional protection against erosion. Number 4. Overturning and sliding resistance. The foundation must resist these two critical failure modes. Engineers calculate safety factors to ensure the wall's long-term stability. For example, in the Dubai Metro project, deep pile foundations were used to support retaining walls in areas with sandy soil and fluctuating groundwater levels. Key stability checks. Number 1. Overturning. Lateral earth pressures create a moment that can cause the wall to tip over. The resisting moment from the wall's weight and base slab counteract this. Number 2. Sliding. The horizontal force exerted by the soil can push the wall outward. Friction between the base slab and foundation soil, as well as passive resistance from the soil, provide stability. Number 3. Global stability. This examines the stability of the entire slope, not just the wall. Deep-seated failures involving the soil mass beneath the walls are considered. Softwares like Plexis or GeoStudio is often used to model these stability checks, incorporating real-world soil and load conditions. For example, the Malampaya gas platform in the Philippines relied on retaining walls with rigorous stability analysis to withstand typhoons and seismic events. Settlement and deformation. Settlement and deformation are inevitable in retaining wall systems, but excessive movement can compromise performance. Types of settlement. Number 1. Uniform settlement. Occurs evenly across the foundation and is generally manageable. Number 2. Differential settlement. Uneven settlement leads to crack, tilting, or structural failure. Deformation. Horizontal deformation can occur due to lateral earth pressures exceeding the design limits or inadequate reinforcement. Monitoring techniques. Number 1. Inclinometer. Measure lateral movement of the wall over time. Number 2. Settlement gauge. Track vertical movement of the foundation. And number 3. Automated total stations. Provide precise measurements of deformation during construction. For example, during the construction of the Three Gorges Dam, real-time monitoring systems were implemented to track settlement and deformation in the retaining structures. Constructability and sequencing. Constructability focuses on designing walls that are efficient to build while meeting engineering and environmental requirements. Number 1. Site preparation. Clearing vegetation, grading the site, and establishing access for equipment. Temporary shoring may be required for steep slopes. Number 2. Foundation work. Excavation is done to the required depth and drainage systems are installed. Foundations are constructed with precision to avoid alignment errors. Number 3. Wall construction. Reinforcement cages are assembled and placed. Concrete is poured in layers with proper curing to prevent cracking. Maintenance and inspection. Even the best designed retaining walls require regular maintenance to ensure safety and longevity. Inspection checklist. Number 1. Structural integrity. Look for cracks, tilting, or bulging of the wall face. Number 2. Drainage systems. Check for blockage in weep holes or drainage pipes. Number 3. Soil conditions. Access for erosion, settlement, or vegetation growth that could impact wall performance. Maintenance practices. Repair cracks using epoxy injection or grouting techniques. Replace corroded reinforcements or anchors in anchored walls. Clean and repair drainage systems regularly to prevent water accumulation. Conclusion. In conclusion, retaining walls are indispensable in modern engineering. They stabilize slopes, manage water, and create usable land in challenging terrains. Throughout this lecture, we have explored the types and functions of retaining walls, key design principles including soil mechanics, drainage, and stability, practical considerations for constructions, maintenance, and inspection. By combining rigorous engineering analysis with proactive maintenance, we can ensure that retaining walls remain safe, efficient, and sustainable.